Okay, welcome to the last lecture of today. I realize that I'm standing between you and a very nice party with lots of drinks later on. And we all already had some drinks now, so I hope you can roughly stay awake in the next hour. I'll try to be as quick as possible. And I will try to give you an overview of deep learning applications. So this is very much an application-driven talk, in contrast to the previous talk, which showed very nicely a number of different methodological techniques. I'm going to show you how you can apply these techniques to a number of medical imaging problems. And hopefully some of these problems are similar to what you're working on and you might be able to use as well. So before I start, I want to highlight a few things which I think are quite important. And a number of things I already mentioned in the last talk, which I gave on Monday actually. And one of this is actually, in the past, it was actually quite difficult to get very large medical imaging data sets. But now, if you really look carefully around what's available for you to actually play around with, there are a number of huge data sets publicly available, and I would encourage you to take a look at these data sets and play around with these data sets. One of them is, for example, something called the UK Biobank, which is a cross-sectional study, which means they're going to recruit everybody or a cross-section of the population, and they're going to not only collect imaging data from them, but also a lot of extra data, for example, clinical records. Their goal is to image over 100,000 people. They have already imaged over 25,000 people, and all of this data is in the public domain. So if you want to play around with this, you can actually get very large data sets and play around with them. If you look a bit more carefully what is included in a data set like this, they include full body MRI, so you can actually study every organ system you would like to study. In addition, they have dedicated imaging for the brain, so you can, for example, extract very detailed information about the anatomy of the brain, but also the function. And if you wanted to, for example, play around with graph convolutional neural networks, all of this data includes fMRI. So you can deduce more than 100,000 brain networks from this data set. They have cardiac imaging, and I'll show you some more examples of this later on. They're not only static imaging, but actually dynamic imaging. And more importantly, they collect a huge number of information about the lifestyle, so how much coffee you drink, whether you're smoking, what your body weight is, how much sugar you take in, to genetic data, as well as clinical records. And Andrea was, for example, showing you earlier examples of multimodal data sets, how you can use multimodal data sets to pre-train your models. This is really a multimodal data set, so you can think of what the computer vision people do in terms of using annotations, using, for example, captions or so. This is effectively what we have in medical imaging. Information about lifestyle, genetics, clinical records, and quite a lot of this data might be, for example, free text data. So you can use, for example, natural language processing here. I should point out that it's more difficult to get hold of the clinical records because they also have more identifiable patient information. But nevertheless, this is a huge data set, and it's great to sort of play around with that. Now, in terms of deep learning applications, we can one thing which I think is quite useful is to sort of think about the pyramid. Where can I actually plug in machine learning to help with automating certain tasks in radiology? And if you start at the lowest level, actually, even when you acquire the data, there's a lot of scope for actually playing with using machine learning, in particular deep learning, to help with making this process either better in terms of producing better quality images, or making the process faster by allowing the imaging to take place much faster, which is much more convenient for the patient. So there are a number of applications. In this domain, we can improve the images by, for example, deblurring them, by using super resolution techniques, and I'll show you some examples of this later on. The obvious thing which everybody will know is sort of semantic image interpretation. That means I would like to localize organs, I would like to segment organs. And then as we go higher in this pyramid, you basically creating more and more value for the clinician, not necessarily for the patient. We can quantify tumors, we can detect diseases, diagnose diseases, which you might think is actually the ultimate aim, but I would actually say really the ultimate aim, the magic bullet of machine learning, if it would exist in medical imaging, would be to take your image and actually making a prediction of that you will have a disease before it's actually really clearly visible for the human. So make actually a prediction and make that prediction in a personalized way so that you can actually do something about this. So all of this is very interesting applications, and I'll show you a few of them. I wanted to remind you of one key element which we're going to use throughout these examples, and that is these CNNs, which are effectively encoder-decoder networks, where we effectively put an image in, we get an image out, or a variant of this image as output, and we effectively pass it through this neural network, doing convolutions, effectively contracting information and then expanding the information again. And many of the examples I will show you, not all of them, but many of them, will use this type of approach in some variant. It's also worthwhile to remember that there's sort of two very frequently used architectures which are used here. And we'll swap a bit between them. The first one is what probably is more familiar, what people in the computer vision community are very familiar with, the fully connected, the fully convolutional neural network from Long, which takes your image, analyzes the information and reducing the information before upsampling, for example, the semantic segmentation. And this is slightly different to the UNet approach from Ronneberger, which has a very similar looking architecture, but what they do is instead they upsample the feature maps rather than the segmentations. It's not a huge difference, but actually it's actually a very sensible thing to upsample the feature maps, and again it's something we can use in a number of different applications. So here are the four sort of areas of techniques which I want to show you and highlight a bit what are sort of the challenges for deep learning if you apply them to these different applications. And I want to start with image reconstruction. First explain you a bit what is actually the challenge, then show you actually a pre-deep learning approach to this, which actually works surprisingly well. The deep learning is not necessarily that much better in terms of quality, but it actually is much more clinically useful, and you will see later on why. So let's start with image reconstruction. So the data set we're going to use is something called MR imaging, and similar challenges exist for PET image reconstruction, CT image reconstruction, for almost all forms of tomographic reconstruction, except that the imaging physics is going to be slightly different for every different application. But nevertheless, all of what you see here, you can apply to CT imaging or PET imaging. So here is the problem. MR acquisition is very powerful but inherently slow. And as long as you image the brain or you image some bones, that is not a problem because your object is not moving and you can spend 5 minutes imaging it. But if you have something which is moving, for example the heart, or you're breathing, your abdominal organs will constantly move up and down, or you image, for example, something such as a fetus inside the mother, then actually you end up with problems. Now, traditionally, the MR imaging people have two solutions for this. The first option is to image as fast as possible and go to real-time imaging. And you can actually get to real-time imaging, where real-time means really you can image 2 or 3 frames per second. So it's not quite what we would call normal frame rates. But the problem is you can only acquire 2D data at best, and the image quality is usually much worse than if you acquire conventional imaging. The other option is to use something which we call gating. And gating works very well if you have an object which moves periodically. So your heart, unless you have atrial fibrillation, your heartbeat is going to be very irregular. And I can look at the ECG and I can work out where I'm currently in the heart cycle. And I can actually create an image from multiple heartbeats. And similarly, if you're breathing, your breathing motion is typically fairly regular. I can measure it with a belt around your chest, for example, and I can basically collect the information across different breathing or different breaths to reconstruct an image. The problem is that you're making the acquisition very, very long if you do this, because you have to wait for being exactly in the right position to acquire more data. So here's an example. For example, this heartbeat is an MR image of the heart, and you see this really looks great in terms of contrast. You have a lot of contrast between the blood pool in the left ventricle and in the right ventricle, and you see the muscle very nicely. It's all great. But this is not a single heartbeat. This is approximately 10 to 15 heartbeats, and the image is reconstructed as an average of these 10, 15 different heartbeats. And it doesn't look very blurred because actually the ECG gives you enough information to trigger in the right moment to acquire more data. But the problem is, you just have to wait for 15 heartbeats to get this image instead of just one heartbeat. So it would be much nicer if we can image very quickly and get all the information in one single heartbeat. And why can we not do this? Well, I want to give you a very simple view of how an MR system works. And I'm not going to talk any physics. We're not going to really touch the physics. But I want to highlight that you're acquiring data in an MR system in something called the k-space domain. And what is a k-space domain? It's just the Fourier transform of the image. So what we're actually measuring is, we're measuring frequencies in this k-space. The lowest frequencies are going to be here in the middle, the high frequencies at the corner. And the only problem with the MR system is I can measure in one direction very, very quickly because of the MR physics. But actually moving from one line of k-space to the next line unfortunately takes some time. And that time, in order to traverse the entire k-space, means that I have to actually spend a certain amount of time collecting all that information. After I've done this, the reconstruction is almost trivial if you use sort of fully sampled data. You simply apply the Fourier transform to get back to your image. Okay? Very simple. Now, if you do this dynamically, so first of all, the reason why this is slow is because I have to sequentially acquire one line after the other. I cannot do this in parallel. There is something called parallel imaging, but it doesn't mean that you're acquiring these lines in parallel. It's actually a slightly different technique. But even worse is if I have a dynamic object such as a heart, I have to keep on doing this over and over again for every frame of the sequence I want to reconstruct. And that means it's even slower, but there is also a huge amount of significant temporal redundancy here. Okay? So what is the simplest possible way of acquiring the data faster? So there's a very simple idea. So if you think about this, if I'm currently acquiring for every frame a full k-space, then the simplest way of making the acquisition faster, what would be the very naive, simple way of making it faster? Anybody got an idea? What could I do? Skip lines, exactly. So what I can do is I can randomly skip lines, and you see in every frame I randomly skip different lines. And I'm not sure how well you can see this on the projection, but I can still recover an image here. But this image has a lot of sort of ghosting artifacts in it. So if you You might not see this very well on the projector here, but if you show this to a clinician, they will tell you you can't use this image for diagnostic purposes. It has all these artifacts in it. So we can now set up a very simple problem which says, well, ideally we would like to do this, because if I only acquire 25% of the data, I'm going to image 4 times as fast. That means the patient only has to be a quarter of the time in the scanner. And the challenge is now, can I, for example, take this data and can I recover the fully sampled image, or something which is as close as possible to the fully sampled image, by using, for example, a machine learning technique. And we're going to start with something which is called compressed sensing, which is a machine learning technique, but not yet a deep learning technique. Okay? So our goal is to go from this image to this image. Okay? There are a few caveats here, because this image is not going to be a scalar image. It's going to be an image which will have complex values in it. And I would like to recover this. So if you look in the literature, this has been known for a long time. So compressed sensing is in a single processing community, has been around for more than 20 years, and Candace and colleagues have really made a very nice mathematical theory on how this works. And in the MR imaging community, it's also very well known that you can use something called compressed sensing to do this. More recently, a lot of these approaches have switched away from pure compressed sensing, and instead they use machine learning approaches. And I want to show you very briefly in how the two approaches differ. So the key difference between the classical conventional compressed sensing techniques and these ones here at the bottom is the type of prior you're using. In compressed sensing, you typically use an assumption of sparsity in some domain of your signal. And these sparsity priors are generally very, very generic. They just basically involve the L0 norm or the L1 norm. In contrast to this, the approaches down here, which we'll discuss a bit more in detail, they effectively learn what is the best prior for your data, what is the optimal way of doing this. Okay? So what does sparsity have to do with all of this? The key idea here is, if I take my data set and I have no artifacts in my data set, I can put it through a sparsity transformation. Let's call this S. And after I've sparsified it, I can basically represent it using a number of coefficients, but the number of non-zero coefficients which I need to use are going to be very low. Okay? So I only need a small number of non-zero coefficients. And the most common approach for using this sparsity transform is to use, for example, something like a wavelet transform. Okay? I basically put this image through a wavelet transform, then I can discard most of the wavelet coefficients. And actually, this is what you're typically using every day if you're using wavelet-based, for example, or DCT-based JPEG compression, for example. It's basically the idea of compression. I can compress my image very efficiently using these models. Now, the image here below this actually has aliasing artifacts, which you probably can't see. Even I can't see it from here on the podium. But that means it has a lot of noise-like structure in the image. And because this noise is almost random, that's why it's so disturbing for the human eye, it actually becomes much harder to compress this data set. So if you apply a sparsity transform to this data set, you need many more non-zero coefficients to represent the data. Okay? That's the key idea of sparsity. And the idea is now that obviously the top image is a good image, very sparse, and the bottom image has a lot of non-coherent artifacts and therefore is not sparse. And what I can probably do is I can maximize the sparseness of my data. So in compressed sensing, I would basically set up the problem as follows. I have my undersampled observation in K-space. I have an undersampling Fourier operation, and I'm looking for a solution X, so the fully sampled K-space, so that it's consistent with what I've measured in k-space. So for every measurement in k-space which I've made, my recovered k-space needs to agree with it. And secondly, I would like to make it as sparse as possible by, for example, minimizing the L0 norm, or perhaps in practice the L1 norm. Okay? So now this is an optimization problem which, given an image, you can try to solve. And this optimization problem simply starts with your initial reconstruction and hopefully will maximize sparseness by finding a maximum sparse reconstruction, and hopefully that's your right image. So that's classical compressed sensing. Okay? This has been known for a long time and works pretty well. Turns out, though, it works pretty well. It's not quite as optimal as you can make it. And the reason for this is that this sparsity transformation which I'm using, I have to specify a priori. So basically, it's a user choice. You as a user, you'll decide, actually, you know what, I'm going to use this particular wavelet transform. But that might not be the optimal sparsifying transformation for your data. So there are a number of approaches which have, for example, tried to learn what is the optimal sparse transformation. And these approaches typically use something called dictionary learning. And I want to highlight a bit sort of how this works with dynamic data. So this is something which we did sort of pre-deep learning. The basic idea is very simple. I take my reconstructed image. I directly learn from this image a dictionary, and you'll see in a moment what the dictionary is. I use this dictionary in a sparse way to reconstruct the image, and then I basically make the image consistent with the measurements in k-space I've made, and I'm going to iterate this process. And I'll give you a bit more detail how this works. So the first step is I'm simply going to extract, I'm first going to learn my dictionary. So one thing which is important is this dictionary, even though I have the word learning in it, it is learned from the data which I'm trying to recover. So it's actually not learned a priori. It's learned from the image you're trying to reconstruct. Basically extracting column vectors from the image, which are sort of patches in the image. And I've drawn this image here as a sort of 3D image, but the third dimension here is time. So the third dimension is time. I'm basically writing this as all these patches in a huge matrix. And then my dictionary learning problem can be written as trying to recover a dictionary D, which multiplied with a set of sparse coefficient vectors is going to approximately recover these patches from the image. Okay? So that's the optimization problem I'm trying to solve. When you learn this dictionary, these dictionaries look pretty much like this. So I'm showing you here the dictionary which we have learned, and what you see here as flickering is effectively the third dimension of the dictionary elements, so the temporal elements of the dictionary. And you can see that these look like not too dissimilar to what you would get when you use, for example, atoms which are built from a DCT or a wavelet transform. So actually using the wavelet transform was probably not a bad idea, but I can basically adapt my transform even better when I learn the dictionary. Once I've learned the dictionary, I can then go to the sparse coding step. And the idea of the sparse coding step is effectively it works as a denoising operation. So what I'm going to do is I'm extracting a patch from the image using this patch operator here, and then I'm effectively minimizing the distance between this patch and its representation from the dictionary multiplied with a coefficient vector. And what happens here is, turns out that representing these aliasing artifacts in the images is incredibly difficult with this dictionary. And therefore, you effectively denoise the image. And finally, after I've denoised the image, I want to make sure that the image is still consistent with the measurements I've made in k-space. So in contrast to a computer vision problem where you say, actually, I want to have an image which looks really clean, I not only want to have an image which looks clean, but I also want to have an image which represents a patient's anatomy. I'm taking my image, I'm going back to K-space, and I'm basically combining my measurements or my reconstructed hypothesis with the existing K-space. I'm blending it together, and then I go back to image space. So this step here means that for those lines in K-space which I've not acquired, so the top bit here, I'm basically using my best estimate. And for those lines of K-space I've measured, I'm blending them with my estimated K-space, depending on this variable v here, which tells me how noisy my K-space is. So if the K-space is completely noise-free, I would of course just keep my original K-space measurements, and I would just choose this to be very large. So here's an example of how this looks like in practice. So what we're starting off with is we're starting off with this image, which is 8 times undersampled. So you can hardly see that this is a cardiac MR image. This is a fully sampled data set, and we iteratively denoise this image to recover this image here. Okay? And this is sort of the closest competitive compressed sensing technique. If you look at the error map here, again, you probably can't see this very clearly, but the errors with the dictionary learning are much, much lower than they are with a sort of standard compressed sensing technique. And you can push, actually, the nice thing is you can push this compressed sensing very aggressively. I can undersample by a factor of 12, so I've only really collected less than 10% of the data. My original data set really is now completely unusable, but the dictionary learning still can recover quite a lot of the image content with high fidelity. You now see a bit more errors popping up, but in the standard compressed sensing technique, you actually now have quite a lot of errors occurring. So this is quite nice, but it's all sort of pre-deep learning. So now you might ask, so how can I should be able to, everything you know normally about deep learning means if you would apply deep learning to this, it should work better, correct? This is what we've all learned. So in deep learning, I can do exactly the same thing. I can set up in principle. My problem is I have my undersampled data, and I want to recover my fully sampled data. And even nicer, I can generate my training data for free if I have a lot of fully sampled data sets, because the way I generate these undersampling patterns is by simply taking the fully sampled data set back to K-space, omitting part of K-space, and going back to image space, correct? So I can actually generate training data very efficiently. The only caveat which I would make is you have to keep the complex reconstruction results rather than just the magnitude of the Fourier transform. Okay, so let's look at this if we set it up as a deep learning problem, because it's going to look slightly different, and you'll see hopefully later on why it looks slightly different. So in the deep learning approach, my idea is I would like to reconstruct this image X. It's basically a set of complex values. So even though we operate in the image domain, remember that if you take K-space, complex numbers, to the image domain, you get a complex image in the image domain as well. And what we typically finally do is we take the magnitude or the absolute value, but we're actually going to keep the complex measurements. We're going to assume that, again, FU is our undersampling Fourier encoding matrix. And then effectively our reconstructed image and our measurements are related by this very simple equation here, where E is the acquisition noise, and this is our undersampling Fourier operation. Okay? Very simple setup. And now if you assume that you undersample on a Cartesian grid, which is mathematically the easiest to do, but not necessarily the best thing to do from an MR physics point of view, but it doesn't really matter because you can easily transform from one domain to the other. I also have this undersampling operation I can write down as a Fourier transformation multiplied with a sampling mask. Okay, so M is this undersampling mask which I have. And then what I'm trying to recover is I'm trying to solve an optimization problem. This optimization problem I can typically write down as having some form of regularization plus some form of data consistency. And actually, the slightly counterintuitive is here which part is going to be done by deep learning and which one is going to be done in a traditional way. So this regularization term typically would be your L1 norm or your L0 norm in standard compressed sensing, and this is your data fidelity term in K-space. So for us, what we're going to do is we're going to formulate the problem slightly differently, and you can see that in our case, the regularization comes from the deep learning approach, from a convolutional neural network which tries to learn a reconstruction of the image. Okay? So this effectively now takes our regularization form. We have trained it. We try to make it as close as possible to X, and then we also have a data fidelity term. And I'll show you how you can do both at the same time in your training. So the data fidelity term we actually also express as a layer in the CNN. And the idea is very similar to what I showed you with the dictionary learning. We're going to effectively have two parts in this equation here. Those parts of K-space which we have not acquired and those which we have acquired. And we're going to basically fill those with the Fourier encoding of the reconstructed image, which is produced by our CNN. You see the CNN in a moment, but effectively the CNN is trying to estimate an image. We go back to K-space, and then we fill K-space either with the result of this, or we blend it as in the previous version with the original zero-filled K-space. Okay? So the neural network which we now have has two sets of layers in it. The first set of layers are these blue layers, which are nothing else than denoising the image. Okay? So they're effectively convolutions, and they're learned convolutional filters, which are simply acting as denoising terms on the image. However, after you have gone through this bank of denoising, you have no guarantee in principle that your data is still consistent with what you have measured in K-space. So the next layer, these green layers, effectively go back to K-space and make the data consistent with the K-space we have. So the important thing is the neural network operates on the image in image space, but it operates on complex numbers. But the green layers actually go back to K-space and go forwards and backwards to K-space. And one of the nice things is that the transformation between image domain and K-space is a Fourier transform, so it's a linear transformation. So I can forward propagate through it, but I can also back propagate my error through these Fourier layers. Okay? So this is a very simple thing to do. I mean, it involves a bit of math, but I can back propagate my errors through these data consistency layers. Okay? So here's a result. This is a six-fold undersampled image. The dictionary learning reconstruction, so the classical learned sparsity approach, the CNN-based approach, and the ground truth. And you can see that all three do a pretty good job. Here's one with an 11-fold undersampling. You probably can't see this, but now this one looks quite considerably better than the dictionary learning. It still looks very close to the ground truth. And of course, you can also do a numerical sort of evaluation, how well does this work. Turns out, of course, as expected, the dictionary learning does significantly better in terms of PSNR. But actually, that's not what's so clinically important. What's most important is the dictionary learning, the sparse coding method, takes around 6 hours to compute. Now, in the test time, when I use a CNN, I only have to make it forward pass, correct? So this can be very fast. These are quite old numbers on GPUs, but you can basically do this in real time. So not only is a CNN much better in terms of PSNR, it's orders of magnitudes faster when you deploy it, which is what actually matters in a clinical setting, because there you want your image to have, you want your image to be reconstructed very, very fast. So the only downside in this approach is that this is a relatively deep cascade. So you've seen that I have these layers of of denoising layers, a data consistency layers, and then again more and more of the same. And if you know this type of architectures, you immediately think about, well, hang on, I should be able to do something cleverer than this. So, because you're basically trying to do an optimization. Effectively, the deep cascade does an iterative process of an optimization. And sort of classical optimization, you try to recover your image, you solve an optimization problem, typically over a different domain Z, because you have regularization and so on. You recover your optimal parameters, you make it data consistent, and you keep on iterating this. And that's exactly what we have done in our CNN. We've basically unrolled this into this long, deep cascade. But that means I should be also able to do this iteratively with a recurrent neural network. Okay? And the recurrent neural network, which we're here using, is quite interesting because it does actually two different, it unrolls this problem in two different ways. If I show you this, this classical approach which we had before, which you saw on the previous slide, we unroll it in terms of time because we have multiple time frames in our cine sequence. So here is one unrolling where we unroll for different time frames. But we can also unfold the different iterations effectively, the different iterations of the optimization process. And so we can sort of solve these two problems with the same recurrent neural network and simply learn one recurrent neural network to do this much more efficiently. And here's an example of this. So this is the recurrent neural network. It's doing basically the same thing as our standard neural network, which is 3D because it has 2D plus time. But the key difference here is this has an order of a magnitude fewer number of parameters. So it's much easier to optimize and it's much faster to optimize. So if you have a problem where you, for example, doing iterative optimization, or you dealing with time series data, I would really encourage you have a look at these recurrent neural networks because they do the job very nicely. So the next problem I want to show you is image super resolution, which is somewhat closely related to this because actually if you think of this as k-space, then actually what is the difference between the previous problem I showed you and this problem? Well, in the previous problem I had randomly sampled my k-space. If I want to do super resolution, I basically make the assumption that I've only sampled the low frequencies and I want to fill out the high frequencies. Okay? So I'm basically now trying to estimate the high frequencies. But I'm not going to do it in k-space. I'm just going to do it in the image domain. So I've told you that I can acquire my data with all these fancy techniques I showed you previously much faster, and I can do so, but I'm still limited to acquiring 2D data plus time in one single shot of acquisition, which means that if I want to make a truly 3D picture of the heart, I have to acquire lots of slices using the technique I showed you before. But if I stack these slices together and view them as a volume, you actually see that in the third dimension, this volume has very low resolution because each of these slices is relatively thick. That means the in-plane resolution is quite high, but the slice is probably 8 millimeters thick. And that means you get a very blocky image. Obviously, with all the things you have learned by now, you know this is a super easy problem for a deep learning network. You just need some training data where you know how your 3D image looks like. You need some data which matches what you actually have. You can actually, fortunately in this case, generate this from the 3D data because actually I can simulate almost every part of the acquisition process very easily. If I know the point spread function of my acquisition device, I can basically take this data, blur it with the right point spread function, downsample it, I get my low resolution data, and now my super resolution model just needs to basically invert this process. Okay, that's, yes? So the problem is that I'm not acquiring this as a 3D K-space. Each of these acquisitions, and you'll see this in a moment, each of these slices is a single breath hold. So basically, I'm acquiring the 3D data in multiple different acquisitions. Now, this ground truth 3D data set is actually a single 3D acquisition with a 3D K-space. The problem with this, it takes you around 40 seconds of breath hold to acquire this data. So perhaps most of you can still do this. If you have heart disease, you're no longer able to hold your breath for 40 seconds. So you're absolutely right. In principle, I could do it with this 3D data. Okay? So if you look at this Mikai paper from 2 years ago, it shows you how you actually potentially upsample the images. But there's an additional problem which I want to highlight, and it relates to the question which we just had. So because I have to acquire this data in multiple separate breath holds, so basically you're lying in the scanner, the radiographer or the radiologist will ask you to hold your breath for 5 to 10 seconds, you acquire one slice, you allow the patient to breathe, and then you acquire the next slice. You keep on asking them to do this. Now, if you do this, there is no guarantee that you hold your breath in exactly the same position, because, I mean, you hold it wherever you hold it, and if you're a patient, if you're quite sick, you probably do whatever you can do. That might mean that actually some of the data might not be acquired in the right position. So that actually, for example, this slice here, let's assume I can only shift the slice in the plane, might be actually in a different position to where it should be. And if you look at the reformatted image now, you can easily see that there are two slices here where actually the data doesn't quite seem to fit in 3D. Now, the great thing about deep learning is it solves every problem. It will also solve this problem, except if you apply super resolution to such data, you get an image like this. Now, if you show this to a cardiologist, they will wonder why you're still alive, because you have a number of holes here in your heart and your heart wall, and this heart can't really work based on what the machine learning has produced. And it's not really the fault of the machine learning, because you give it actually data which is inconsistent, correct? So that's a challenge. So we thought about is, can we train a neural network to actually have a more anatomically informed prior to do something clever? And turns out if you can do that, hopefully we can generate, even though with this inconsistent data, some useful data. And one of the reasons why we identified we have this problem is that we have a cross-entropy loss, or our loss function, which we typically use. Let's say we do segmentation, we typically use cross-entropy loss. You're basically summing over all the pixels in the image. Or if you do super resolution, you have an L1, L2 loss. It's a pixel-wise loss. There is no information about an anatomical prior in there. So we thought about a network architecture which takes a low-resolution data set which has potentially these artifacts and simultaneously produces high-resolution images and high-resolution segmentations, while being able to handle this in this inconsistent data. And the way we do this is, hopefully with all the things you have now learned, not too difficult to see. So we first train a network which we call, or which is actually not our invention, is called the TL network, has been used in computer vision by a number of people. And sort of the network has sort of two components. The first component is some form of effectively an autoencoder. You take your segmentation input, you encode it into a latent space with a very low dimensionality, you have a decoder, and you recover your original label map. Okay? So actually, in some form, you can almost think of this doing PCA on your segmentations. Yeah? This is in some form, PCA would be the simplest possible autoencoder you can use here, a linear one. Okay? And we simply have a convolutional autoencoder here. But at the same time, we train another network which tries to predict this latent code, H, directly from the intensity image. And we're trying to minimize here the difference between this latent code H and the prediction of the latent code, and we update this network according to this error in the latent code. Okay? So we have this sort of this TL, we call this a T network because it sort of looks like an inverted L, but in some cases we only involve the L branch here for evaluation. So how does this network help you? Well, let's look at how we now train our segmentation network. So our segmentation network is trained with low resolution input image. It gets, we have a high resolution, it produces a high resolution segmentation output, and it does so by minimizing the cross entropy to the ground truth. Okay? So this is your standard, this would be absolutely your standard segmentic segmentation. Your segmentation network produces a segmentation, you compute the error in terms of cross entropy, you update your segmentation network, and you keep on doing this. But at the same time, we take the segmentation output, we put it through the encoder, the first part of the autoencoder, produce a latent code, and we do the same thing with the ground truth segmentation. And now we minimize, as a second quantity, the Euclidean loss of these latent codes in this latent representation. And so this tries to make the segmentation similar in whatever latent space you have to the ground truth labels. And so if you, for example, now go back and say, actually, forget about this being an encoder, or let me assume this is just converting the image into PCA representations, you're basically saying, I would like this image to have the same representation in PCA space or some other latent space as a ground truth segmentation. And that's more difficult if you have inconsistent segmentation. So this is the segmentation part. And it turns out it works really well. I'll show you some more examples in a moment. But you can do the same bit with the super resolution path. You're going to basically now predict your super resolution model. It's going to predict a super resolved image. You minimize the L1 error to your ground truth high resolution image. But you're also doing this, again, this other minimization of the latent space error by putting the image now through the intensity part of the predictor, predicting the latent code, and doing the same thing with the ground truth labels. Okay? So, and this is what this produces. So this is in the original low resolution image with some inconsistencies in it. This is what your standard super resolution model would look like if you only have your L1 error. This is what the anatomically constrained super resolution looks like. And this is what the high resolution ground truth image looks like. And you can see it actually does a pretty good job. And again, you can do this with time series data to actually make this algorithm even more robust. Okay. So I want to now move to the third part of the talk, image classification. And this will be fairly quick. I'm just going to show you some very simple application of classifying images of video sequences for medical purposes. The project which we're doing this as part of is something called iFind, and the idea is very simple. We would like to build a system for automatic fetal screening. So if you're in the UK, if you're a woman in the UK and you're pregnant, you typically have 2 standard examinations of the fetus, one at 12 weeks, one at 20 weeks, and they're really there to look for abnormalities and make sure that you spot any abnormalities. And ideally, we would like to automate this abnormality detection because it's quite difficult to do this. And we have a fairly large collaboration with industry and a number of different universities trying to do this. So the task which we have as a classification problem here is a very simple problem in principle. It's basically saying what is in this image. So this is a 2D ultrasound image from a video stream, and we would like to say that this is a view of the baby, and it's shown the abdomen of the baby. And if you show it a different frame, for example, should say, well, this shows the lips of the fetus. And by the way, if you ask me where the lips here are, I've looked at this image many, many times, and the sonographers have shown me many, many times where the lips are. I still can't see this in this image. And so the idea is, can we do this in real time on an ultrasound machine? Okay? This has a number of applications. I'm not going to talk too much through the applications, but of course, with all the things we have learned, you know that this is a standard, effectively, something very similar to ImageNet. I have a large number of classes, and I want to classify every input image. So we have a neural network architecture, which is quite simple. A key thing is it produces spatial feature maps at the end. So we have k different classes, typically around 17 or 18 classes, and we produce feature maps which are 13 by 13 by k, and then we perform the final classification using a global average pooling followed by a softmax to basically have an activation for one of these 17 classes. And the reason why we do this is because we want to do it in real time. We were quite lucky that we had a lot of data to train with. We have data from 2,700 patients, and you have to realize that the data is all in video sequences. So these are 2,700 patients with more than 20 minutes of video. So there are a huge number of frames in there, and we have around sort of between 1,000 and 5,000 labeled data sets for every class which we want to identify. So here's a sort of demo of this system working. So what you see here at the bottom is basically the different classes being shown which video sequence this is. So it's probably a bit hard to see. This is a brain view, which is shown here. So the probability goes up here very high for the brain. It will come to some other views at the moment. So this is an abdominal view. But most importantly, if you look at this number here, you can see you can do this easily at 120 frames per second. So this is much faster than what you would need to do this with. So that you can really do this very easily in real time. But one thing which is also interesting, if you analyze what the system has actually learned, you can actually also now use this to basically get the system to tell you where the object is, which it recognizes. So let's assume, for example, this image here shows you the 4-chamber view of the heart. So the label is called a 4-chamber view. And this class here has been activated. We can now go back to the feature map for this particular class. It's a 13 by 13 feature map. And we can backpropagate which pixels are activating this feature map. Okay? So we can basically now backpropagate the activations and create a sort of saliency map in the original video. And using the saliency map, which is a very simple form of a saliency map, we can effectively threshold that and detect where the object is. And the nice thing is you can do this without having trained the system by telling it where the object is. We only tell the system what the object is in the image, but not where it is. So what you see here is some of these saliency maps and how you can use them for object detection. So effectively, this is sort of the object detection equivalent to computer vision. So here you see, for example, that if it's a spine view, the saliency map is a spine. Here, 4-chamber view of the heart. You see the beating of the heart in the 4 chambers. And then if you threshold this feature map, which you will see in a moment, here's a femur, so the bone in your leg, you can see that you can detect the object with very simple thresholding, correct? And you can still do this at very high frame rates. You can still do this in real time. And I think this is quite a nice example which shows you that if you have a lot of training data, you can really solve these problems very well. Now, why is this also a useful problem to solve is, well, one thing you can do this is nowadays a lot of people use not only 2D ultrasound, but also 3D ultrasound. Now, if you have a 3D ultrasound probe, that's great, but with a 3D ultrasound probe, the sonographer no longer sees all the data because you're acquiring a 3D volume. What part of the data should you actually show to the sonographer in real time? Well, one idea is you can actually extract these standard 2D views directly from 3D volumes in real time and show the sonographer the sort of classical views they've acquired, but at the same time you've acquired a whole 3D stack of data. Good. I think I'm nominally supposed to finish now, so I will. We started a bit late, so I will go very quickly over the last bit and leave you enough time to prepare for getting to the party on time. So the last bit is image segmentation. And you might say, well, we've learned almost everything about segmentation, semantic segmentation. I've showed you already an example. I just need a simple network like a fully connected network or UNet, a lot of training data. I showed you this particular case from UK Biobank where we had 5,000 subjects, nearly 100,000 2D views. If you do this, you apply your network to this data, works really well. You compare it to a manual observer and you can do it as well as an expert. Not better, but as well as an expert. So that's solved. Now, I'm sure that many of you have done this before. They've come up with a very nice working algorithm. So this one should solve now all cardiac MR image analysis problems. But what happens quite often is you go to your clinic and suddenly your algorithm which you have trained in the lab no longer works quite in the same way. And there are a number of different reasons for this. You know, you might have different scanners across different hospitals. You might have different scanner protocols, different sequences. Of course, also your patients might vary. And sort of the standard machine learning approach is you go back to your clinical collaborators and tell them, sorry, it didn't work. You just have to give me more data. Just annotate a few thousand more images. And then they all will appear very quickly like this. They get very angry. You told me this was solved before, and now you want me to do more work. So they don't really react very well to this. So how do you solve this problem? I want to show you one particular way how you can solve this problem using adversarial neural networks, combining classical CNNs with adversarial neural networks. And really this tries to solve a problem which many of you will know as a transfer learning problem. Correct? I've trained my network on data from one domain, but I wanted to also work on data from a different domain. So the extreme scenario is you might take a VGG pre-trained model. You would normally not assume that it will work directly on medical data, but you will basically update the model a bit. But of course, that requires you to have labeled data. So I want to show you an example where I can actually train my model using data from one domain only, but still make it robust to the test domain for which I have no labeled data. Okay. And just to take a quick look into what we're actually trying to solve here is this practical problem is the following. Let's assume you have some labeled data on your source domain. You have some crosses, you have some circles. Obviously, you can do a pretty good job by learning this classifier, which is this line here, okay? Now, in your target domain, where you want to deploy your algorithm, if you would have some labeled data, you would actually realize that this in the target domain, because, for example, it's a different scanner, it produces data with slightly different characteristics. The crosses are here, the circles are here. If you would have known this in advance, you would have learned a better classifier, because these cases all now get misclassified. And a better classifier would have been this line here, which does a reasonable job on the blue points, but also a reasonable job on the green points. Okay, so this is a classifier which is robust to data from both domains. Okay, so how can we learn this if we don't know for this domain, for the target domain, which ones are crosses and which ones are circles? Okay, so there's a very simple idea which comes from adversarial learning, which goes as follows. Well, let's assume I can learn a second classifier, a domain classifier. And this classifier, its task is not to distinguish between crosses and circles. Its task is to distinguish between the green points from the target domain and the blue points from the source domain. And I'm also going to tell you that I would like to minimize the accuracy of this classifier. So what does this mean? Minimize the accuracy of this classifier. That means actually I want to have a classifier which cannot tell the difference between the green points and the blue points. This might really look counterintuitive. It was proposed in this very nice article 2 years ago. And you will see in a moment what the rationale for this is. And remember, if I want to learn this classifier here, I don't need to know what are crosses and circles. I only need to know whether the data comes from the target domain, the green one, or from the blue domain. And that's typically relatively easy. For example, if I have two different scanners, I can actually look at the DICOM header and I can work out this is a Siemens scanner, this is a Philips scanner, correct? This is not very expensive to do. Okay, so here is now how you can use this. So remember that I've proposed, I've done some shameless self-advertisement of this deep medic neural network, which was developed in our group, which does brain segmentation, but can also do many other segmentation tasks. It has this sort of convolutional layers which analyze the image at full resolution and at low resolution. It can do really nice things, such as brain segmentation. I've shown you all of this. I just like the movie to show you this once more. And how do we now make this robust to data from different domains? So what you probably see is that I still have my traditional segmentation approach here. You see that I have two different pathways here, the full resolution pathway and the low resolution pathway, and they produce a segmentation. So this green box here is exactly the standard deep medic neural network. But what I'm also doing is I've added this bit here at the bottom in this red box, and I'm basically taking some of the features which a neural network produces. So the intermediate feature maps, I put them into another convolutional neural network, and that neural network tries to classify whether the data comes from, let's assume, a Siemens scanner or a Philips scanner. Okay? And so now the rationale of trying to minimize the accuracy of this discriminator is that effectively this discriminator uses the features which a neural network has learned. If the features which a neural network has learned are completely invariant to both domains, then this classifier will fail miserably. And that's what I would like to do. I would like to learn features in these feature maps which are not related to whether the scanner is a Siemens scanner or a Philips scanner. Okay? At the same time, I still need to minimize my standard loss function, which means I would like to have a good segmentation. So if I basically backpropagate my error from the standard loss function, my cross entropy, and I backpropagate my errors from the domain discrimination, but they will go through the entire neural network, also through the branch which deals with the segmentation. Okay? So really what you can think about this is that you have two loss functions. The first loss function is here in this green box, and it's your standard cross-entropy loss function, with the only caveat that it will only, this branch, you'll only be ever able to evaluate with the training data for the source domain you have, because you don't have labeled data for the target domain. But the bottom branch here, this domain discriminator, you can evaluate for all the data for all the data you have. Okay, so you can't really calculate these loss functions for all the data, but this one you can only compute for your source data, and this one for the source and the target domain. And if you do this, I'll just show you an example here where we have not simulated that we have different scanners, but we have simulated that we have different imaging sequences. So in one case, the source domain, we only had I think a gradient echo sequence, and in the target domain we didn't have the gradient echo sequence but a susceptible weighted imaging domain. If you train a network and you don't make it domain invariant, it will really fail quite miserably. But if you actually have a domain invariant network, it actually will still perform quite well, even though I've swapped one imaging sequence with another imaging sequence. Okay? Good. So the last, I'm not going to spend more than 5 minutes, I promise you. I want to show you just one other approach which you can use. You've probably seen that there are a number of different segmentation networks you can use. Deepmatic, fully connected networks, UNets. So you have lots of different network architectures, which is great. But you also have a lot of meta parameters. How many layers you're going to use, how you're going to train this, and they all influence the behavior. And you really have to do with trial and error finding out what is the best model for your data. There's an alternative approach, which is goes back to something really well known in machine learning, is if you want to build a really strong classifier, why not take multiple potentially suboptimal classifiers and combine them. This is something which we called EMMA, which we used for a MICI challenge last year for stroke segmentation. And the idea is very simple. For example, if I take this flare image, I have a manual ground truth segmentation. If I now train my neural network using cross entropy or dice as a loss function, I'll get different results. And I don't really know which one is necessarily the best one. So what I'm going to do is, instead of learning one model, we're going to basically try to approximate the distribution over all the different models, because we want to factor it out, because we're not really interested in it. So the idea is that we're actually going to compute an ensemble classifier which takes multiple different classifiers as input. And so, for example, in terms of different network architectures, you might use Deepmatic, FCN, UNet. Plug them all together, you learn all of them. You can learn them with different depth, with different width, with different training loss functions, different sampling strategies, and so on. You plug this all together, you stir it all around, and then magically you can go to your next MICI challenge, and you can automatically win it without really putting any intelligence into it. So of course this only really works if you take this quite dumb approach, and I would really call it a dumb approach because it's a brute force approach. But if you have enough GPUs and if you have enough colleagues in your lab who work with you, it actually works very well. It's a quite interesting approach. Good. So I want to sort of come to some summary and conclusions. You've already seen deep learning in a number of different applications. There isn't really an application yet there which shows you that you can actually reduce or replace the human in the loop. So you can't really replace your radiologist yet. And really, one of the things which we have barely touched yet on, which I think is something we need to all work on, is if you're a clinician, you're never only going to look at images. You're always going to look at patient information and patient records in order to make a decision. Okay? So validation is extremely challenging. You really need to work in a team together to make this work. And really one of the things I want to highlight here at the end is if we can do end-to-end training, we've actually not done this yet in the right way. And I want to show you in an example why this is. So at the moment, we optimize acquisition, we optimize reconstruction, we optimize analysis, but everything is optimized separately. Correct? The paradigm of deep learning tells you, well, actually, why don't you do this as an end-to-end pipeline? Correct? Why don't I actually optimize the whole process, train it together end-to-end? And while we're at it, why don't plug in some additional data sets as well? I want to show you something which we're going to present in a month's time at MICAI, which sort of tries to do this in a first step. And the idea here is simply, again, you probably can't see this very well. This is a movie of the heart, with the heart being segmented into left and right ventricle and myocardium. And we want to see is, can we actually recover this segmentation without reconstructing the image? If I know in advance I'm only interested in the segmentation, can I acquire my images more efficiently? So for example, can we recover the segmentation of the case space, which is overlaid here on the ground truth image, from 20 lines of case space, which is actually this raw data, from 10 lines of case space, or even from 1 line of case space? And it turns out, if you use temporal redundancy very well, you can even get from 1 line of case space, you can get a pretty good idea of the segmentation of the heart. Now, why is this useful? It's because at the moment, all the reconstruction, or the entire imaging pipeline is designed to produce images which are optimized for a radiologist to look at. But they're not optimized for a computer to look at. With this approach, we're basically trying to optimize the acquisition so that the computer can, in the best possible way, extract the heart automatically. Now, this is not useful if you want to find a tumor in the image, but if you want to measure the volume of the heart, this works. So this will not produce as a byproduct an image reconstruction, which poses a lot of challenges for how do you validate this or how do you detect whether it still works, but it's a very interesting approach, and it basically tries to optimize the whole imaging pipeline. So I want to stop here, acknowledge all the students and clinical collaborators and postdocs in our lab who worked with us here, as well as the funders. And in case anybody has a question and doesn't want to run off to the party yet, I'm happy to answer any questions. Thank you very much.
Thank you, Daniel. I wanted to ask about MR fingerprinting. Basically, at what stage is this technology? Is it useful, and how it can be used with deep learning?
So Michael asked a question about a technique called MR fingerprinting. Some of you might be familiar with this technique. The basic idea of this technique is not only to undersample case space, but also to undersample the possible image acquisition parameters. So you can actually reconstruct from your data every possible imaging contrast. So a T1 contrast, a T2 contrast, and you can produce quantitative measurements. Now at the moment, there's a lot of work on MR fingerprinting proving that as a proof of principle, it can work really quite well. I have not yet seen, for example, any application of MR fingerprinting to dynamic data, so most of the work is done on the brain. And in almost all the cases, you can see that the image quality is not quite there as with a conventional acquisition. But of course, a conventional acquisition takes much, much longer to do. So in principle, these integrated reconstruction pipeline could be applied to MR fingerprinting, and you can then basically optimize one neural network to recover one parameter, such as a T1 parameter, and one to do the T2 parameter. But at the moment, I haven't seen any approaches doing this yet, and I'm not 100% sure what the limitations are in that space.
Is there any question? One more, last one.
I was just wondering that these compressive sensing techniques, whether they can be used directly with little or a lot of modifications to remove metal artifacts from medical images?
Whether they can be used to remove artifacts?
Metal artifacts. You talked about removing other artifacts, but can they be used to remove metal artifacts provided we have no idea what could be behind them?
So I think you can, the compressed sensing techniques in principle, the theory basically tries to estimate missing data. And so the problem is, for example, in these approaches which I've showed you, the metal artifact is in the original data. So if you make, for example, if you have a data consistency term, you would violate the data consistency if you recover an image without the metal artifact. So I think if you wanted to use these type of techniques for artifact reduction, you would probably need to first have also an approach which identifies the artifact, and then basically you can say in these regions I can relax my data consistency term. But for example, in the approaches I've shown you, we basically assume that the data we have measured is actually correct. That means it's true data. So our model would always try to recover that metal artifact, and you couldn't really train the model to not do that.
Okay, let's thank again Daniel. Thank you very much.